VISTA, Vent Intelligent System for Temperature Adjustment, Senior Design Group 34, sponsored by QZ Sun. What is VISTA? VISTA is a vent system that combines the inexpensiveness of traditional heating/cooling methods with the sophisticated technology of a smart thermometer. VISTA employs temperature, occupancy, and humidity sensors to detect and respond to environmental changes, thus improving the efficiency of airflow in a home or building.
This is the main components board for VISTA. Our current testing progress for it consists of successful integration of software through the ESP32 and the USB UART bridge, which is through the CP2102 chip. The labels shown indicate the main parts of the board as well as all of the peripherals. The humidity and temperature sensors are housed on the actual board, while the PIR occupancy sensor is a separate board that is externally connected through a set of header pins, and then the servo also has a set of header pins for separate connection purposes. This board is fully soldered and functioning with code, and it successfully receives voltage from our power board. The power board uses a 9-volt battery that connects through the wires shown. 2 voltage regulators, as labeled, step the supply voltage down from 9 to 3.3 and 5. Everything runs on the 3.3 volt except for the servo, which runs on 5. Additionally, the PIR sensor can technically run on either 3.3 or 5 and is still undergoing testing. Finally, the main components board connects to the power board through the header pins shown.
The PIR sensor board is fully soldered and is in the process of reevaluation due to an issue with our current schematic. This issue and our solution will be discussed later in this video. While the output is still in the trial phase, the rest of the board has been probed and tested and is working accurately. The board also is fully powered by our power board and is communicating sensor data with the main board correctly. The humidity sensor is working very well. It is placed on the main board and is accurately showing the humidity of the room it is activated in. As you can see in this video, our humidity sensor is reading 48.19 and the thermostat of the room is showing humidity at 50. This is an error range that is well within what is needed for the scope of our project. The next step for the humidity sensor is to become integrated further into the decision-making side of the software. The temperature sensor is also on the main components board and is working correctly. The sensor can also accurately communicate its data readings with the ESP32 module. As you can see in the video and photo, the temperature comparison of our sensor and the thermostat are well within the accurate error range. The temperature sensor has already begun to become integrated into the decision-making process side of the software. This will be elaborated on later in this presentation. Final back-end implementation of the sensor will be required for the final demonstration. The servo motor is working as expected. When asked to turn 90 degrees in one direction or the other, it will accurately turn. The servo is also currently integrated with the temperature readings, so when the temperature is below or above the desired temperature, it will turn accordingly. The servo is also able to continue turning in one direction if one rotation is not sufficient enough for opening or closing the vent. The next step for the motor is to have it be able to interact with our final prototype.
As for the actual mechanical design, we don't have a working prototype at the moment. We've mostly just been focusing on the PCB and software side of things. But the intent is to have a rack and pinion system similar to the one pictured here, where we'll have the servo attached to one of the driving gears that'll open and close the system on top of the vent, which hopefully will provide like an airtight seal, which will increase the efficiency of the overall design.
Send data to specific endpoints hosted on the ESP32. For the device configuration, it must receive the Wi-Fi SSID, enterprise configuration, Wi-Fi password, Wi-Fi username only if the Wi-Fi network is an enterprise network, the device name, and the user login and password. The video will showcase the ESP32 successfully retrieves this information. As showcased earlier, all sensors in the servo work standalone by themselves. Test programs have been written to ensure that they work as expected and can be integrated into the VISTA software stack. On top of this, the device logic for when to open and close the vents has also been started, firstly by opening and closing the vents based on the current temperature reading and the minimum-maximum temperature variables. As well as this, the PIR sensor has also been successfully integrated into the software stack. This means that the PIR sensor can be read from the front-end web page, and the ESP32 successfully communicates the PIR sensors via endpoints through either a direct front-end communication or through a back-end relay. What is still left to do is to integrate the rest of the sensors in the servo into the software stack. More API endpoints need to be constructed so that the Vista web application can successfully control the servo to open or close a vent, and also that the web page can read the current temperature and humidity status. The backend will also need to be updated to allow for a possible backend relay for the remaining sensors in servo.
Currently, the PIR sensor board is able to interact with the rest of the design. Right now, it's receiving power and outputting a signal. However, our original design is not fully functioning as intended. The IC on the PIR board is supposed to output a digital on-off signal if motion is detected or not, but unfortunately, it's not working for reasons not fully understood at the moment. We're currently working on a workaround to essentially capture the ADC value of the sensor itself and then handle all that digital logic internally. Now for our 3 key engineering specs. Our first metric is the room occupancy accuracy. We want to detect if there's a person there 90% of the time when the person is there. This is not in regards to like a false alarm rate or anything like that. The second metric is our response time, which we could have a very long response time if we wanted to conserve battery, which is one of the constraints of our project. But we think a reasonable responsivity would be about 5 minutes or less than. And then our final metric is the network range, where many existing solutions similar to the Vista require you to be on the actual vent to interact with it, pushing buttons or using a near-field Bluetooth communication device, which using a network will open up the possibility of doing it remotely, and I think this is one of the specifications we targeted. As previously mentioned, the room occupancy PIR board is not fully working as intended right now, so these results are based off our readings from actually just measuring on one of the pins that outputs an amplified and filtered signal from the raw sensor. We still need to make sure that this accuracy is maintained once we implement it and add some state machine logic to control if we are actually detecting somebody or not. But across various distances, 0.1 feet to 6 feet, we were able to detect occupancy, motion, or just the presence of somebody every single time.
As shown in the video, the servo motor is accurately able to get the data from the temperature sensor and then rotate 90 degrees. This inherently will open or close Vista's vent slats to change the room conditions. To test our vent specification of fully opening or closing the vent within 5 minutes, we conducted 10 different trials of the servo motion. This 5-minute specification may seem long based on our trial results, but the added time is assuming that the final prototype of incorporating the physical system and responding to multiple sensors will add some resistance, causing delays. Based on the trials we have done, you can see that the servo is working much better than expected, as it is opening and closing at a rate of approximately 5 seconds. This is well below our expected rate, and therefore it is predicted to pass the design specification of the final project.
For the engineering specifications, we chose to test the Wi-Fi functionality on the ESP32 with varying distances. We decided to use the device configuration process as a means to test the network connectivity between the ESP32 and another device, as this was easiest to set up. This device we chose was an iPhone, showing that also the web page loads properly on varying devices. Note that the iPhone was first connected to the Wi-Fi access point directly next to the Vista device, and then the device configuration web page was loaded at varying distances away. First, the web page was loaded directly next to the Vista device, which shows the success as seen from the picture. Now I proceeded to walk 15 feet away from the Vista device and reload the web page. As seen from the video, the web page will still load just fine. Next, I walked approximately 50 feet away from the Vista device to an outside room with walls obstructing the Vista device and the iPhone. As seen from the video, the web page takes slightly longer to load, but still successfully loads the web page. Finally, attempts were made to load the device configuration web page from a further distance, including outside of my apartment, introducing more walls and obstructions between the Vista device and the iPhone. This connection typically failed, but was included in the calculations to determine the failure distance. This procedure was done 10 times to calculate the average failure distance of 55 feet.